Hello, myself Srinivas.
And myself, Vibhum Singh.
We are a team from IIST. We are going to present our computer vision project, which is regarding camera calibration, color correction, and glare detection and removal. So, in this project, we are mainly focusing on removing the distortion and color variation coming due to uh, the OED cameras.
OEM cameras that are original equipment manufacture cameras, and those images from those cameras are not processed, so the output has many distortions like fisheye distortions, and the colors are usually not very accurate. So for different application we need um, accurate colors and undistorted image. So for that we process that image through OEM solutions. So we are making that.
So the first problem is the fisheye lens distortion. In this problem, we use a checkerboard to find out the distortion matrix, K matrix and D matrix, and try to undistort the photo. Uh, we are so we have a video of a fisheye distorted checkerboard. So this is the coordinate transformation model which we are assuming, and
So we use checkerboard for camera calibration because it has high contrast. So the corner detection is easy, but in the algorithm we are not actually using corner and normal corner detection tech techniques because it has mainly in accuracy, and it will detect corner from outside the checkerboard also. So we use something like quadrilateral fitting, and we first identify the black and white areas, and then we try to fit quadrilateral in that images. We know that we are correcting the distortion, so there will be some distortion in the quadrilateral also, but we allow some distortion. But if the quadrilateral is very distorted, like it is concave, so we will reject it. So
Because of this, it also works on circular grids. That is one circular white and one circular black, that kind of stuff. And this is the requirement for detection. We want 15 to 20 image. Instead, we have a whole video of checkerboard distorted. And XIJ is the grid coordinate system, that is the world coordinate system, assumed world coordinate system. And here it is also assumed that the z coordinate of all the points are same, so that is actually ignored. Also, the corner detection process, as Vibhum Singh told us, is finding out uh, the finding out where the squares are intersecting, the white and black squares, and we use subpixel corner refinement, which gives us subpixel level accuracy. In this, initially we find out x naught and y naught, which is in integer terms, and we take a n by n window around this x naught and y naught, and then find the intensities of the neighborhood, and use the gradients, and we find that uh, gradients, and use Taylor series expansion and find out the extremum in that region, and we again form another window around that newly formed position, and this process is repeated until the error is too low, and based on the error which we are taking, which is too low, the accuracy may vary like zero point 0.1 pixel to 0.01 pixel. So these are the intrinsic matrix, which is the camera matrix, and the distortion is due to radial and tangential distortion, and the radial and tangential distortion can be calculated like this, where k1, k2, k3 can be found out using our code, and also p1, p2 also. These are radial distortion coefficient and tangential distortion coefficient, and when this distortion coefficient are varied, the distortion is varied, and we are going to find out we are going to find out these values. So this is the result of the distortion. So this is undistortion, I mean, and this is the distorted image, and this is the undistorted image. So
We define the input parameters, and these input parameters are global variables, and main function is defined, and in that we define the width and height of the image, and the grid size of the uh, checkerboard, and the grid points are calculated using the grid size of the image checkerboard, and object points and image point variables are defined, and uh, while true, we are going to read the frames in the video, and every time when we read the frame, we are going to convert it into gray frame, I mean grayscale, and calculate the corners using CB2's draw chessboard corners, and CV's find chessboard corners, and once to check if the checkerboard is correctly identified, we use the draw chessboard corners to find out to show the points which are found. Also, after that, when we after that we calibrate the images using the obtained matrices. So now we have corresponding points on image plane and real world points, and using these we are going to perform the calibration. Then we calculate calculate K. We first define K and D matrices. K is a 3 by 3 matrix and D is 4 by 1 matrix, as I shown you, and we use the calibrate function in CV2 fisheye to give we input the object points and image points. This object point and image point contains all the points from all the frames, and W and H, as defined earlier, is width and height of the frame, and K and D are inputs, and now, when we do the fisheye calibration, we get the K and D values, and if the return is true or false. So, if the return is true, we write the file and save it in YAML the parameters. So, as you can see, for the given video which we have chosen, I mean which we have produced, these are the parameters. So this is the D matrix and the K matrix respectively. This is the K matrix. You can see there are 9 variables, and there are 4 variables here. So yeah, these are the matrices, and this is the output video. This can be seen. And this is the output video. Now, if you see the input video, just like this. This is the input video, and this is undistorted to get that output video.
Color correction. So the video that we got from the OEM camera has color inaccuracy, and in various field we want the color to be very accurate. Uh, the color processing can be of two type, one which focus more on color accuracy and one which focus on the image should look pleasing also, like Oppo camera, and not a very accurate image. So here we are doing it for color accuracy. So what we are doing, we are using standard checkerboards like this, which have standard color that we know, and here are their standard RGB values. So, and in here it is what we uh, get the color from that videos, and here are the correct colors in the left side, and we are making a linear assumption that there exists a matrix that can transform it. We are using this matrix model, so it will be easier to implement in hardware using many matrix multiplication methods like systolic array and etc.
So for this matrix, what we do is we can take A matrix and find out, point out all these values, like the RGB values, which are given in our distorted and video, which is directly got from the OEM cameras. And B is another matrix which can be predefined using those values. Vibhum Singh showed those values can be put inside. And one thing what we did is we used multiple number of multiple values of the same palette, so that the error is averaged out, so that there is no random error. And so, and at the end, M is what we have to calculate, and it is calculated by this formula. This is an approximation. So in the so that is what we are doing, and this is the initial image, and this is the image after we corrected it. So as you can see, there is some brightness decrease in here, and also the color is changed very ever so slightly. So now let's see the code. This is the code implementation in which we are using the color correction function and the getM function from camera calibration module, which we have made. So this camera calibration has many functions, namely getK, which gives a distortion matrix for fisheye distortion, and the another function undistort, which uses the K matrix and D matrix got from getK to undistort it. And there's the extract frame function, which is used to get a particular frame number. If you give the frame number, it will give the particular frame in that video. This is useful in many places where we want to get every 5 frames of the video. And this is another function which is called apply color correction. In this function, we just make them color correction. We give input image and color correction matrix are given inside. So it will give us the corrected image as output. And this function getM is used to get the color correction matrix. In this, what we do is we print out the frames, and let's run this code and wait for it to come. So when you run this code, it generates a video path and save file path, and N is got from getM function. In this getM function, what we do is we read the frames from the videos, and here it is set up as for every 40 frame for 100 frames. So 100 frames are actually loaded in background, and they will be shown one by one. You can actually change it using n pe next and previous, and then select the function using your mouse cursor, and also save the point using S. So as you can see, the click event, it identifies the XY coordinate that is in the pixel, and to the find out the corresponding value from the image matrix, which is the image itself. From the image matrix, these values are saved in a matrix as we show as we have shown, A matrix, that is the RGB measured matrix. B matrix, which is the RGB measured matrix. And as I told you, we are selecting 5 points for every color. So we are totally 120 points should be selected. And these RGB measured values are saved in this RGB measured matrix. And the base colors is the RGB reference values. These values are saved in base colors. These values are available online. And RGB reference is the matrix which has five times each of these values. That is 115, 80, 82, 68 5 times, and then so on and so forth. Everything 5 times, so that it can be matched directly using matrix multiplication. And then these RGB references, as I told you, like 5 times repeated. And then distance matrix. Now we don't know which color we are selecting first and which color we will be selecting later. So what we do is to find out which color is what. We use distance method. Like we find the Euclidean distance between measured matrix and measured and reference values for like each and every measured value. We find distance from all these values, all these reference values, and we make them such that the least distance ones are mapped together. This is assuming that the values are very close to the real values. And then using this arrangement, the matrices are redefined. This ordered matrix is used for the calculation. Now, as you can see, we can see this pop up. In this, we can see all these matrices. This is the video. These are the frames. Are 100. There are 100 frames that are read by the code. These are frames from our video, which is uncalibrated. So as you can see, pressing N, you can go to the next frame, and pressing P, you can go to the previous frame. And once you get to a particular frame, you can select one point, and you can see it is prompting us that it is patch 1 is recorded, and the X and Y coordinates are also printed. Now to save this point, you have to just press S, and the patch is saved and the patch number is updated. Similarly, you have to do 5 times for every palette. And now I am just going to quit this because I have done this already and it will take some time. So after this is done, as I told you, it will order it and measured and order the measured matrix, and then find out the camera color correction matrix, and it is actually saved in the color matrix.csv. And then this color correction can be done using video path, M, and save path. These are the input for it. So if you give the video path and save path and color correction matrix, the color correction matrix is saved in color matrix.csv. So this will give you the output video, and also it also saves it in the save path. So yeah, that's about color correction. Now now as we can see, there is some glares on the image, which is also affecting the color detection, and this color correction is not very accurate in looking. So what we did is we tried to remove the glare from the image, and for that we did two approaches. One is using HSV approach, that is the hue, saturation, and value approach. The glare pixels are defined as pixels with high brightness and low saturation. That is, V is approximately 1 and S is very, very less than 1. And the thresholding is done manually for some time. And then we also trained a model, machine learning model. We also tried to train a machine learning model and find out the glare portion and remove the glare. So the results are these are the results. As you can see, this is the input image, and this is masking done by HSL. And here you can notice the problem that the saturation of the palette colors are low in this case and very high in this case. So it is not so accurate. So like this, we tried to tune it and remove the patches here. And the masking done by ML method is like this. We train the machine learning model, and the ML method gave similar masking, and the declaring is actually a problem here. So it is not declared very successfully. So these are the things we have done. Thank you.